Okay, hello everyone. My name is George Pappas, and I would like to talk to you today about safety and robustness in deep learning using semi-definite programming. This is joint work with my postdoc Mahir Fazliab and Manfred Morari. And I should also thank Sagar for organizing this invited session. It's too bad I cannot be at Denver, and I'm hoping this video will give you a little bit of a sense of some of the work we have been doing. So there is no question that in the past decade, there has been a revolution happening in the area of deep learning, which has clearly impacted the areas of computer vision, computational linguistics, and speech processing. And it's slowly finding given visions of autonomous and self-driving vehicles, and as well as potentially using machine learning and deep learning for control and action. However, despite these tremendous advantages and compared to the state of the art in computer vision, when it comes to the area of self-driving cars, there has been a very recent realization that we are not there yet. This is a very recent article from the IEEE Spectrum that's saying that we were promised 5 years ago that this year we will be having self-driving cars, and the cars, autonomous cars, are not there yet. And we cannot blame just deep learning for this. There's a lot of other things that need to happen. This is a very challenging problem. However, the sensitivity and fragility of deep learning is one of the many things that one needs to address. And this is the topic of my talk today. So despite the tremendous advantages and improvements in deep learning, around 2015, one of the realizations that came more from the computer security angle is that one can very easily fool deep learning systems by adding these very carefully crafted artificial noise. So here you have an image that goes through a neural network and tells you that it's a panda with some confidence, and then you add this noise that has no physical meaning, and you add these two images, you get another image that gives you a gibbon, and the neural network thinks it's a gibbon, and not only that, it actually thinks it's a gibbon with a much higher confidence than before. So it is very easy to fool by crafting this artificial noise, but it's not just related to artificial noise. One can add, for example, artificial patches on a stop sign and an image of the sensor, and then you can misclassify a stop sign to be a drive with a speed limit of 45 miles an hour, but also natural variations, which could be that it just got darker, and because it got darker, we are not able to sort of detect using some neural network which way to go, or detect certain obstacles, making it easy perhaps to drive in some times of the day, but very fragile to drive in other times of the day. And until those sensitivities are addressed, I think the self-driving vehicles will be a reality, not a reality. So this is the problem that I'm going to focus about. I'm not going to talk about self-driving cars, but the issue is the fragility of deep networks in general, where we can think of a multi-layered deep network, and I'm going to get into this later, where we can have deep networks. You can think of these as compositions of linear and nonlinear layers like this, where at the input, you put some image. You can think of this as a huge vector or a matrix of very large dimension. You put your data in, and it's evaluated through the neural network, and you get some binary label that says stop. But then what happens is that you take the same image and you add some carefully crafted noise, and you push it through, and now this is misclassified not as a stop, but rather as another symbol that says you can go through this with speed limit of 40, and of course that could have catastrophic consequences when you're at an intersection. So the question is, how do we understand this? How do we analyze this? And maybe in the future, how do we make this more robust? So the class of neural networks I'll be talking about in this talk are the classical feed-forward deep networks, which could be modeled as, here we have the input, which is our data, and we'll have a certain dimension. It goes through a linear layer, and the linear layer usually is actually an affine map of the form, which are the linear weight matrix times your data plus some offset or bias term. And then you go through these nonlinear activation functions, and then you get another sort of vector, and then you keep doing this again and again and again, and then usually at the end you get the evaluation of the data through this neural network. So you can also look at this neural network mathematically in this form, where you have L layers, and x0 is your initial condition, or if you like, the data point. And then you go through this sequence of linear maps composed with activation and nonlinear activation functions. And of course, the classical activation functions going back to a long time ago are sigmoidal, but more recently, people have resorted to the so-called rectilinear linear unit, or this piecewise linear kind of function for a variety of reasons, which are outside the scope of this talk. But there's a zoo of such activation functions we can all discuss. Okay, so this is a mathematical abstraction of a neural network. Now, how can we make neural networks more robust? And there are two main paradigms. One, you can think of it as an analysis, and the other one, you can think of it as a design paradigm. So the design paradigm is what is known as robust or adversarial training. So here you are given a set of data like this, and you're trying to classify it, meaning you're trying to find for a classifier that separates the data from to stop sign or go through sign. However, a lot of this data could be perturbed adversarially or through nature by a little bit. So every data point here can be perturbed by a little bit, using some kind of a norm bound. And then what happens is that, some of the data points can cross the surface when you perturb them this way, leading to these so-called adversarial examples, like the panda becoming a gibbon and so on. So the way to defend against such attacks is to embrace what is known as adversarial training, where you take the data, you add some perturbations, and you try to the adversary first is trying to maximize the loss function that you use in the classification. And then what you're trying to do with a neural network is figure out the parameters or the weights that are minimizing the loss function for the worst case variation in the data. And this is what leads to these types of curves, which provide defense against these adversarial perturbations, where the adversarial perturbations are bound to be these polytopes or something like that. So this is this is how you train a neural network to be robust. That's not what I'm going to talk about today, even though it's a very interesting direction that I'm working on. Today, I'm going to focus more on, to some extent, on the inner maximization here, which is after you have trained the neural net. And then you can think of it as essentially as a nonlinear map, that you have some kind of an input here. You have an image. You may artificially perturb the image or naturally perturb the image. The image may be perturbed by artificial or natural noise. You push the image through the neural network, and you want to ensure that when you push the output is to some extent classified the same way, or it stays within certain safe bounds. And that's essentially the way that you certify post-training the safety or the robustness of the deep neural network. So there's no training here. The training has happened. Somebody gives us the deep neural network and says, can you show that this post-trained neural network is robust to changing the data a little bit, how much can this be? So this is the problem that we're going to be talking about. I'm happy to talk offline or online about the first problem. So when you look at the verification of neural networks, this is an area of research in a variety of communities. There has been a lot of work in the computer-aided verification and in the formal methods community, but also in the machine learning community, and now a lot more in the control community. So I would classify those approaches as two main broad paradigms. So there are the first paradigm, which really started with the reduplex work at Stanford, has to do with taking a feed-forward neural network with a ReLU nonlinearity and sort of converting it, if you like, into a mixed integer linear program and posing the safety or the analysis of input-output properties of it as a mixed integer linear program. And the advantage of those approaches for ReLU networks is that they are exact, and the disadvantage is that they are not as scalable. Okay? So because of every time you have a ReLU nonlinearity, you're adding a binary variable. The more binary variables, the more this does not scale. Alternatively, if you don't, a variant of mixed integer linear programming related to it, if you come from more of the computer science and approaches, satisfiability modular theory approaches. Okay, so this is another way of, but all of these are more or less exact approaches. They solve the problem exactly, but they do not scale as well. So the alternative approach is to say that I'm not going to aim for exactness. I'm willing to have some cost or lose some information, but hopefully scale more. Okay? This leads to inexact methods where there have been approaches that look at you can say linear programming relaxations of MILPs or things like that. And to some extent, our work, or what I'm going to be talking about here, falls in the category of convex relaxations of such problems. So we would like to analyze the previous problem using a convex relaxation of a neural network. Okay, and these are some other related works that in this space, and I'll be comparing against some of them later. Okay, so the approach that our group that has been following really goes back to a connection that was established in the 80s between deep neural networks and dynamical systems. You can interpret a post-trained neural network as a dynamical system in the following way. So in the neural network, you can have a data here, and datum here. You can add some perturbations. Okay, so you think of this as an initial condition, which goes through a linear layer, and then you go through a nonlinear layer, linear layer, nonlinear layer, and after L linear layers, you get an output, and then you see where the output falls on the left side or the right side of some hyperplane. Okay, so you can interpret this evolution through the neural network as a time-varying system with nonlinear feedback as follows. So you can think of this as you start with your data point here, and then, this is the input, if you like, to the system, and then you go through the first linear layer. So this would be the first linear layer, W1 and B1. And then you get Y0, and then that goes through this nonlinear activation function, okay, which could be ReLU, it could be tanh, it could be sigmoids, whatever you'd like. And then you go back, and now you're in the second layer, and you go again through another linear layer, and then again through a nonlinear layer, and you do this for L steps. So in this case, L layers of the neural network would correspond to L time steps of this dynamical system. Okay, so evolution of the data through the neural network can be interpreted as L step evolution through this dynamical system, which is time varying because the layers here at different layers are different, and but the nonlinearity is here, component wise are sort of the same. Okay, so this is something that was known. Jan LeCun actually had a paper in '88 or '87 about this. And this is something that we have explored recently, not so much from the perspective of verification, but from the perspective of robust training, because what can happen then is problems of robust adversarial training here can become actually problems of robust optimal control here. And there are deeper connections. And if you're interested in that connection, which is a different direction, I would encourage you to look at our very recent paper that was published last week at the Learning for Dynamics and Control conference, the new conference. So now this is great. We can connect, verification of deep networks to this time-varying nonlinear feedback composition. What's the advantage? Is there any advantage? Okay, so let's go a little bit, so what we would like to do using our approach is to analyze to some extent the sensitivity of the deep neural network by analyzing the sensitivity of this closed loop system. So here x0 would be this data point, but we will perturb the initial condition by a little bit. And we would like to see how the evolution of first the stop sign, where we will land, and hopefully this gets classified in the region that's classified as stop. But then when you perturb the initial condition a little bit, hopefully, we want to see, do we stay in the stop region or do we go outside and are misclassified as something else? So this is very much a sensitivity analysis. And I think the control community has a lot of things to say about sensitivity analysis. In fact, this is sensitivity to initial conditions when you treat initial conditions as data. Okay, so now what kind of tools can we from the control community bring to address this problem? What kind of tools do we have? Well, these are tools that we have been working for a while in our community. So how do we analyze systems that are linear, possibly time varying, but with a nonlinear feedback? Well, one way you could do this is by abstracting the nonlinearity by using the generalized KYP lemma, if you like, or in this case, we'll be abstracting it with a quadratic constraint of this form. So the input-output behavior of this nonlinear activation function is going to be abstracted mathematically by an input-output behavior or relation, more precisely, which is captured by this quadratic constraint. Okay, so this tells us a little bit how these are related. And this is, of course, something that goes back to the original ideas in robust control, as well as more recent ideas about integral quadratic constraints. Okay, so this is going to be the key idea that we'll see throughout the rest of the talk. And the idea, of course, is that we will be paying a price here because we're not exactly capturing this nonlinearity, but rather we're over-approximating it. So we will have to pay an over-approximation price when it comes to analyzing the behavior of this system by getting this system that is no longer has the nonlinearities, but has the convex over-approximations of it. Okay, so what we're going to say, one of the advantages is that you can apply to the zoo of activation functions that are out there, including sigmoids, tanh, ReLU, leaky ReLU, max outs, and all these things. So all these activation functions have a specific structure that can be exploited in the framework that we're going to be describing next. Okay, so what is the key structure that all of these functions have? Well, we know that when we deal with linear systems plus nonlinearity, one thing we always look at is, well, are the nonlinearities sector bounded? And if that's the case, then we can do something. Well, a lot of these functions, the nonlinear activation functions, are not just sector bounded, they're in fact slope restricted, which means that not only are they sector bounded, but its derivative is also sector bounded. And this is precisely what is captured here. So you're basically saying that this nonlinearity is slope restricted on A and B if essentially something that resembles the approximation derivative is between A and B. And this is graphically essentially what this means. Okay, so not only are we in the sector bounds, but the variation of the derivative is bounded. And in fact, you can see that happening in all of these cases. Okay, and what are the different alphas and betas that may depend on the different activation function, but the approach will be applied to all of them. And this is one way you can capture essentially the quadratic constraint for capturing that. And I'll get into more details there soon. So for example, what is the quadratic constraint for the ReLU activation function, the one that is widely used now in deep learning? So then here, the ReLU function, you can write this, for example, like this. So you can write this as y equals the max of 0, x. Okay, now you can decompose this input-output function as the intersection or the composition, if you like, of these three sets. These two sets are convex, so there's nothing to do here. You know, the y greater than 0 and y is greater than x. These are convex sets. The intersection is convex set. However, this is not convex. Okay, so this is an equality constraint. It's not convex. So this is precisely the thing that you need to over-approximate by some convex relaxation, and you can multiply this by any number, positive or negative, and you can multiply this by any positive numbers, and then you get essentially this constraint to over-approximate the input-output constraint of the ReLU function. And this is precisely then the quadratic constraint that can over-approximate the input-output behavior of a ReLU function. So the relationship between x and y here is always captured between, is an element of the set for any lambda, nu, and eta, and which lambda, nu, and eta we will choose is going to be a decision variable we're going to use later to tighten the over-approximation. Okay, this is essentially the key idea. This is how you do it for ReLU, you can do for any other function. Okay. So now going back to the big picture, we have our original neural network. I'm showing it here for one layer, but this applies for many layers. Okay, and what happens is that we don't do anything with the linear layers. Linear is good, linear is scalable, linear is computable. We don't change them here in our approach. But what we do is we take the nonlinear layer here and we over-approximate it by these quadratic constraints I showed earlier. Okay, and the advantage, of course, here is that the input-output behavior of this neural network is strictly contained in the input-output behavior of this quadratically constrained linear or convex network. And the advantage, of course, here is that we can analyze properties of this network using by using semi-definite programming, and that will allow us to scale to levels that is hard to do using MILP directly here or other approaches. Okay, so this is our way of approximating neural networks or convexifying their models, the nonlinear models, and this allows us to, you know, if we can verify proofs, show defenses, you know, compute the Lipschitz constant, get, you know, proof stability here, because this is contained, you know, this behavior of this is contained there, then whatever we can show here, whatever safety properties we show here, they would be strict, you know, they would also be proven there. Of course, this is a sound, but not necessarily complete abstraction, meaning that if we're not able to prove something here, it doesn't mean that it does not hold in the original. It could be that it's an over-approximation and it's a bad one as well. So, but if you do, it's a sound abstraction in the sense that if you do prove that something is robust or safe, or then it would apply also for the original system, something we'll see in a bit. So to give you a sense, you can do many properties. I'm not going to have time to go through all of them. I'm going to pick one. I'm going to talk about how do we think about computing the Lipschitz constant of a neural network. Okay, so this is an important topic, not just in control. I mean, in control, you can use such Lipschitz constants to do small gain type theorems with neural networks in the loop, for example. But it also has Lipschitz constants are actually being used as regularizers in adversarial training in machine learning. But also Lipschitz constants have been shown to be critical in trying to get generalization bounds about the theoretical understanding of deep networks. So there's a lot of reasons why you know, it's important to understand you know, Lipschitz constants, but there are very, very few ways of computing them. And of course, in addition to computing them, the Lipschitz constant is very much tied to this notion of sensitivity analysis, because if you have here a data point X and you perturb it by epsilon, so this could mean, for example, that you vary images at the input by a little bit and you push it out, well, then you can use the Lipschitz constant to get a quick estimate of where all these images would land after the classification. And then you can do a quick test of, for example, whether you're robust with respect to that. So it's a measure of local or global robustness, because There's a version, there's a local Lipschitz and a global Lipschitz. Here I'm going to talk about the global Lipschitz function, which has nothing to do with the data. It's a structural thing about the neural network. So you would apply to any data. You can also do this in a more local way as well. So the point here to keep in mind is Lipschitz constants are important. Lipschitz constants are something that is hard to compute. And then lower Lipschitz, of course, would mean lower, more robustness, because you have less, the noise at the input is amplified less at the output. So we're going to go back to the same story that I was saying before, that we have the original neural network. We'll take the nonlinear activation layers. But in this case, we're not going to abstract it precisely using the quadratic constraints that I showed earlier, because the Lipschitz constant, essentially what it says is that nearby inputs lead to sort of nearby outputs. So here, what we're going to be using is this variation of quadratic constraints, which is incremental quadratic constraints. So there's that small variation, which looks at how the variations in the input and the variations in the output are related, and we have some quadratic approximation of it. So rather than computing the Lipschitz constant of this neural net, which would be what we would want, what we're computing here is in fact an upper bound to the Lipschitz constant. We are computing the Lipschitz constant of this, which is going to be by construction an upper bound to this, to the Lipschitz constant of our original neural network. Okay, so this is essentially, again, the same philosophy of sound abstraction and compute towards a more computable class of models, where we take this neural network and we convert it to this, and it's a sound abstraction, and we compute this function, which of course Q is going to be a parameter which we can choose, and we'll see that later. And then any number we compute here for a Lipschitz constant is guaranteed to be a upper bound for the true Lipschitz constant of the neural network. Okay, and the advantage here is we can compute this Lipschitz constant now using semi-definite programming. Okay, this is essentially what we're doing. Okay, so this is the theorem version of the previous slide, because we like theorems. So if you have a single layer of this, the paper has the multi-layer version as well. If you have a single layer neural network, which you can view it this way, and assuming that the activation functions are slope restricted, like ReUs and so on, and you know what alpha and betas are, then this gives you here a semi-definite programming a semi-definite programming characterization of Lipschitz constants. So if you can find a row that makes this semi-definite program feasible, then the square root of that row is guaranteed to be a Lipschitz constant for the neural network. So therefore, what you would like to do is you'd like to find the smallest, the tightest upper bound Lipschitz constant that is sort of that satisfies this characterization. Okay, so this is the semi-definite programming relaxation for computing the tightest upper bound to the Lipschitz constant of the neural network. And now there are a variety of other related problems, local, lower bounds, things like that. So invertible neural networks and so forth. Okay, so we have tried this experimentally. This is these are the only other approaches out there for computing neural networks are here, if you're interested. Very recent papers also at NeurIPS. This graph here shows that that basically that our approach, we have 3 variants of our algorithm that you can find in the paper, essentially gets the most accurate upper bounds, because it's easy to scale by getting trivial inaccurate upper bounds. The question is balancing the accuracy to scalability trade-off. As we said, the MILP approaches are exact but not very scalable. And then the question is how you can scale without compromising too much on accuracy. So this shows you that at least on the accuracy side, we're doing well. On the scalability side, MILP approaches I have seen go up to hundreds of neurons, or maybe occasionally crossing to 1,000. So here we have, as I said, a variety of two different versions of the algorithm. And the largest we were able to go, and this gives you the computational times for computing the Lipschitz constant, is to go to 500 layers, where each layer, I believe, has 100 activation functions. Okay, so this is about 50,000 neurons, which is clearly pushing the envelope as far as the state of the art, as far as computing Lipschitz constants. But also, but of course, the flip side is that it's very far away from the kind of things that people use in vision. So, so we were able to push 1 or 2 orders of magnitude from what we've seen in MILP, but we are still order of magnitudes away from the kind of things that we see in computer vision. However, I should say that for the kind of deep network architectures one sees in deep reinforcement learning, there, I think we're already within range. Okay, so there you don't see the neural networks are probably in the 2,000–3,000 neuron range. So I think those, if you have a deep neural network and you'd like to verify the safety or compute the Lipschitz constant of it, those now you can compute those Lipschitz constant, and this is on a laptop, not on some GPU cloud infrastructure, in the order of minutes. So. The other thing that is important is, does adversarial learning help? And this is something that, this is when, like if you do a robust control design, does it improve on the analysis side, the verification side? And the answer to this is yes. And these are, the classical, 3 classical ways or standard ways of doing robust learning. ADAM, of course, is the non-robust, the vanilla version. LP-train is sort of a way by you introduce some linear programming defenses to adversarial examples. And then projected gradient descent train is an algorithm that comes out of Alexander Madry's group, which is more, sort of you can have a game theoretic version that I presented earlier. So that's the same. So if you train algorithms with these 3, if you train deep networks with these 3 different algorithms, this is the non-robust and the other more robust, then this tells you, what our analysis tells you is that if you train neural networks using robust training, then that indeed results in lower Lipschitz constants. Okay? And that implicitly then, or directly results in better robustness, because what we did here is we pushed the whole MNIST database through the neural networks and see the misclassification errors. And indeed, for robust training networks, we had lower Lipschitz constants and less misclassification errors when you push the whole database from one side to the other side. I talked a little bit about Lipschitz constants. Very quickly, you can do a whole bunch of other things with this framework. For example, you can do probabilistic verification. So in this case, you may have a data point, but you don't have some kind of a polytopic or some infinity ball around it, but you actually more have some kind of a confidence interval around it. And then you have some distribution and you push it through and you want to compute the confidence interval of the distribution of the output. And you would like then to know, you would like to have some assurance, like I just passed this data point, I think it's a stop sign. How sure am I that this was a stop sign? And you can get now lower bounds on the probability of correct classification by essentially using the same trick that we will, we'd like to know what is the confidence of the true neural network. We'll have the quadratic abstracted network, and we'll compute the confidence interval here, and that will provide a lower bound now on the probability for correct classification and so forth. Here, so it's again the same idea. This is a paper that was presented last year at CDC. And then you can go now from understanding just the neural network to understanding the neural network, but now in a closed loop system. Now, if you have the Lipschitz constant, you can also go small game theorem type analysis, or you can think of this as a a deep network, which we can abstract the way we were abstracting it before, and then compose it with another linear system. And now think about the safety or the stability of the closed loop system. In this case, could be a robot, which takes images, and then you can ask, will my robot reach a particular, hit a particular obstacle? Will it stay within certain bounds? And what you want to do here is verify that the closed loop system, which is the neural network plus the linear system, does this. So simply, by doing the tricks we were doing before, which have to do with abstract this out with this quadratic constraints plus linear in this composition, couple this linear system and do the analysis. And this is essentially the key idea that has been submitted for a conference coming up. So this concludes a little bit what I wanted to say. Going forward, there's a whole bunch of other things we're interested in. For example, scalability, scaling semi-definite programs to the level that computer vision people are interested. To some extent, we started working, as the previous slides showed, on the safety and stability of deep transfer learning. We're also interested in model-based robust learning, and this you can find already on our archive if you're interested. And the motivation for this is very much trying to understand not artificial perturbations of the data, but rather physical perturbations of the data. And this is something, for example, that you can find here or you can find there, which is, you see an object during the day, you classify it, and then all of a sudden the background changes or the lighting changes, and all of a sudden we misclassify something. And that it makes machine learning very fragile, but it's not an artificial attack where you're perturbed by some epsilon, but rather it is some natural variation that actually causes this. So the question is, how do we become robust? How do we train neural networks to be robust against such variation? And this is precisely, we have a new framework which we call model-based robust deep learning, where we have models of natural variation about how lighting changes the data, and then we do adversarial training around such models. And this is one way by which models can help make deep learning more robust. And I'd like to stop here. Many more things that are interesting. Thank you for your attention. And again, thanks to Saga for organizing this. Thank you.